Good morning from London. Good afternoon, actually, in China. I hope you enjoyed your lunch. And together we will have today a short session today. I don't think we will take the full 2 hours or 245 minutes to finish the part on viscoelasticity. I have already planned for some multiple choice questions to revise the contents of mechanical properties. Let me open the light. Maybe that's better. I have prepared a couple of multiple choice questions to revise a bit the mechanical properties. And most probably we will finish slightly earlier today. Let's see. I get a lot of emails from you for the coursework, which is good. I remind you the deadline is this Sunday, so I hope you're all pretty much wrapping up your essays and you're almost ready to submit. I'm looking forward to reading your essays. And what else? Yeah, today we will finish with the delivery, let's say, classes, the classes on the standard content of the course, where we will finish with viscoelasticity. Next Monday, we will have a mock exam where essentially I'll give you, 30 minutes before the class, I will post on QM Plus the test that we will do. I will give you maybe 1 hour to finish the test, and then we will discuss the solutions together. Okay? Of course, this will not count towards any grades or whatever. It will just be a practice for the real test. It will be in the same format of the real test, just to get you familiarized with the exams concept and how is it going to be in the real exam situation. Let me think what else. Yeah, and then of course Tuesday and Thursday we'll be revising the contents from the whole semester. So any questions, please, you can think, please send them over. Of course, I know it's very busy for you to revise at this stage. So that is why I will go through a revision of the most significant contents of the course with you. And we will have one more session, I think it's Tuesday in 2 weeks. Let me see the date. Oh no, I know the date. It's the 7th of December, which will only be a Q&A question, okay? Okay, so let's get started today. In order to finish with viscoelasticity, let's remind ourselves a bit what we said about viscoelasticity, which is a property of the polymers, essentially, because they exhibit both elastic and viscous behavior, okay? And we said that in terms of the viscoelasticity, two phenomena that are very interesting and very practical in using polymers in engineering applications, okay, are creep, stress, relaxation, okay? So, a distinctive feature of the mechanical behavior of polymers is the way they respond to an applied stress or an applied strain, okay? And creep behavior essentially defines how a polymer behaves under constant stress, while in terms of the stress relaxation, it gives us an indication how a polymer operates under constant strain and how what is the time dependence decrease of stress under constant strain, okay? So we also looked upon the two very common models that are used to study creep and relaxation, the Maxwell model and the Kelvin-Voigt model. And we already said that the Maxwell model is most appropriate in studying the relaxation behavior, while the Kelvin-Voigt model, or the Voigt model as it's most commonly named, it's very suitable to study the creep behavior of polymers. Okay, today we will we will be discussing how do we fabricate these creep isochrones, which are approximating stress-strain curves. Let me use blue one. Approximation of stress-strain curves. Okay, and also I will present you with more details about dynamic mechanical analysis, which is a quite sensitive technique that can give us information regarding the transition temperature, and more importantly, the glass transition temperature. And also it can give us information regarding the modulus of a material. It's called storage modulus, but generally it's the same with elastic modulus as a function of time. Okay, how essentially do we produce a graph like this one in a DMA? Okay. Yeah, this is the response to a constant stress. This is creep, and we can see that we apply a constant stress here, and we can see that there is a rapid increase of strain, after the strain increases, then we have some kind of relaxation, or essentially a recovery, or in other words, recovery may be a better word, because the relaxation can also I understand that relaxation can also confuse you with the actual relaxation. Okay. And here, in terms of stress relaxation, we have a constant strain, and I told you we calculate, we measure the amount of stress, the decrease of stress that is required to maintain the strain constant. Okay, and there is a decrease of stress, as we can see in this graph, in an attempt to keep the strain constant. Okay, it is impossible to keep a constant strain without a decrease of stress. Yeah, this is the elastic behavior. All energy that we input is essentially given back to the system, and the excitation and response are identical. And you can see that in terms of the loading and unloading conditions, there is no energy that is lost in an elastic material. Okay, and an elastic material is represented by this spring in those simple 1D elastic viscoplastic models, which we said already that they consist from combinations between springs and dashpots. Okay. And dashpots is a way of a representation of viscous behavior, where essentially all energy that we're inputting in the material, all excitation, all energy is lost. Okay. And as a result, the polymer flows irreversibly under the action of external forces. In this case, the equation that describes viscous behavior is given by Newton's law, which is the viscosity times the strain rate. Okay, this is the strain rate. And finally, we have the viscoelastic behavior, which is a combination of the two. As I told you, it's modeled with combinations between dashpots and springs, and it is the more complex that we try to model this behavior, combinations of dashpots and springs. The more difficult is the maths, of course. And of course, as a result of the viscoelastic behavior, we have parts of the energy loss, not full energy loss. So energy is lost partly, let's say. Let me put that after that. Okay. Yeah, this is the behavior in terms of creep and stress relaxation. In creep, we keep the stress constant and the strain increases. And in relaxation, we keep the strain constant and the stress decreases. And we talked about the Maxwell and void models, which are the simplest one, essentially. In the Maxwell model, we have a spring and a dashpot in series. And in the void model, these are connected in parallel, okay? And we went to our nodes, and as we can see, for the Maxwell model, we obtain this equation for the creep behavior, which, as we understood, it is not possible to describe the creep behavior because you can see that the ultimate graph for the creep behavior based on Maxwell's model is this one. So it cannot be used to study the creep behavior of polymers. While in terms of the stress relaxation, in terms of the stress relaxation, we can see that it is very useful in order to use the Maxwell model because it can quite accurately used to study the relaxation of polymers, okay? Now, the void model. The void model is given, as I told you, by a spring and a dashpot connected in parallel, so that leads to a uniform strain. And as a result, after some very simple transformations of the Hooke's and Newton's law, which I expect you to remember for the exams, we have this equation for the polymer undergoing creep, okay? In this case, I should clarify that τ0 is not the relaxation time, okay? But in this case, it is called the retardation time. Even though it's given by the same equation, okay? Eta over epsilon, okay? This is the retardation time, okay? It is the measure of the time of the material that needs to accumulate the creep strain, okay? Where should I write that? This is a problem we will be discussing later. Let me write it here. τ0 for is the retardation time. Essentially, it is the measure of the time taken for the creep strain to accumulate. So how fast creep strain increases, so is determined by this time. Let me move this a bit. Can I move it like that? No? Anyway, I'll squeeze this here. So retardation time It is a measure of for the time no, sorry, for okay, so essentially we said that for the creep, we apply constant stress when we measure the strain, okay? So essentially it gives us how fast we will reach this, this maximum strain here, this creep strain. So the shorter the retardation time, that leads to a rapid creep strain. This is strain over time. Sorry about the space limitation here. We will solve this problem later together after we finish with the multiple choice question. Okay, and now let's go back to the slides. And besides the Maxwell and the void model, which we discussed already, there are more complex models, as I told you. A model that can be used to account for both phenomena is this one. It's called the standard linear solid model, where we have a spring in parallel connected in parallel with a dashpot and a spring in series. Okay, so this is a standard linear solid model. Why I cannot see you? Okay, anyway, so this is a 1D mechanical models, as we said. Okay, and essentially we already saw that this model is useful for the decomposition of stress in glassy polymers. We will not be going through the mathematics of the standard linear solid model, partly because they're not that interesting. It's just simple substitutions and so on. So we already have established two models that can relatively accurately describe creep and stress relaxation. So in any case, if you will need to use any of the creep or stress relaxation equations for any problems you might need to solve, you can use one of the void or the Maxwell equations. Okay. Yep, this is what we said about stress relaxation. Okay, and as we said, this equation originates from Maxwell's model. Forget about that one and that one. I'm not sure if you have the new updated slides. I have the old ones. That's why I won't be going through these today. Now, let's have a look at how what are these creep isochrones. Okay. Sometimes what we can do is we can perform creep tests in order to obtain the stress strain curves for a material. And these these stress-strain curves, these modified stress-strain curves, as you can see here, this is a stress-strain curve. Make this shorter. Are essentially called creep isochrones, okay? So the construction of creep isochrones essentially is another method for fabricating or obtaining a stress-strain curve for a material. This is too thick. Of course, they cannot at any point substitute the actual stress-strain curves, okay? So let's not confuse ourselves with their efficiency, but still they are an approximation, okay? Sorry. So what do we do in the process of fabricating creep isochrones? Is essentially we perform creep tests, okay, at constant stress, and we said that for creep tests we measure the response of strain over time. Okay, so we have, let's say, we perform a creep test at sigma 1, let's say 1 megapascal, and we measure the response of the polymer in terms of strain over time. So we keep one time, T1, let's say equals to 60 seconds, and then we perform the same experiment, but with higher stress, okay? If we say here we have 1 megapascal, here let's say we have 5 megapascals. So we have a change in the strain over time response, okay? So we take again the same time and we get another E2. So we get 1 point, E1, S1, okay? And then we get a second point, E1, E2, S2. And in this way, we can collect a number of points where we know both the strain and the stress that we apply, okay, at a constant time. And given that we have these data points, we can create a graph of stress-strain curve at constant time. That's what isochrone mean. Isochrones. It comes from the Greek words isos and chronos. Okay, it means equal time, okay? So T1 is always the same along that stress-strain curve, okay? T2 is the same for, let's say, that stress-strain curve, and so on. And that is the way we fabricate the creep isochrones, okay? The disadvantage of constructing a creep isochrone, of course, as you can realize, it takes too long, okay? So disadvantage, and of course it's an approximation, okay? It can never be used to fully substitute stress-strain curve. It's time consuming. Okay? I repeat, what we do is we perform creep experiments at constant stress and we measure strain over time. And at a constant time, we get data points of strain over stress, given that we know both of them, and we construct these creep isochrones. Okay? In the same way, we can fabricate the relaxation isochrones. In this case, we keep the strain constant. Sorry. we fabricate the relaxation curves for different stresses, okay? And for constant times, we obtain again data points such as E1, sigma 1, and so on. And we fabricate what is called, in this case, relaxation isochrones, which have very similar characteristics to creep isochrones. Yeah, we already spoke about that. Essentially, when we apply a certain load for an elastic material, all energy is dissipated. This is an elastic material, and we can see that the load that we put, we get back almost the same, if not all the same energy. Okay, so all energy is dissipated. In terms of the viscous, we don't have any viscous response. We don't have no energy dissipation. Here we have Hooke's law, okay? And here we have Newton's law. And for the viscoelastic material, we have partly energy dissipation. Okay? And we have permanent deformation in viscous response, okay? Deformation. Anyway, we have already discussed this, and this is just a slide to remind you of the behavior of different behaviors of polymers. This is a wrong slide, and that is the reason why I wanted to update those slides. Okay, this is the response here is wrong, so it's fine. And now let's go to dynamic mechanical analysis, which is one of the most important thermal analysis techniques. So we have already spoken about different thermal analysis techniques. With thermal analysis techniques being, let's say, experimental techniques or characterization techniques, which tells us how a polymer behaves under the influence of temperature. Okay, what is the structure or generally the characteristics of a polymer if a certain amount of heat is applied to it. And thermal analysis techniques are mainly those three ones that we discussed: DSC, okay, which we use to measure melting point, crystallization point, and the glass transition; TGA, which is used to measure the decomposition of polymers, okay, and DMA. Or DMTA, Dynamic Mechanical Thermal Analysis, okay? DMA is much more sensitive than DSC in identifying the glass transition and secondary transitions. So in terms of TG, DMA is more sensitive and DSC, as it can also identify secondary transitions such as the secondary glass transition as well. It can identify we have already spoken about a secondary transition called TAF Vita. Okay. Yeah. What do we do in dynamic mechanical analysis experiment? Essentially, we apply sinusoidal stress and we measure the complex modulus. Okay. We observe the response of of our polymer to the sinusoidal stress. What can we do usually is we vary the frequency of the measurement. Let me show you more obviously here. So we usually vary either the temperature or the frequency of the measurement in order to obtain a graph of modulus versus temperature, okay, for different types of material. Now, there are different types of holders that we use, where this purple thing is the, what is the sample? Yeah, the purple thing is the sample. And what we do here in let's say a dual cantilever setup, essentially, is that we move this cantilever up and down, okay? The frequency that we move this cantilever is essentially we provide that frequency, okay? It's usually constant frequency. And then we do a temperature sweep. Okay, so as you can see, these are different sample holders. The sample holder that we usually use depends on the amount of material that we have, and also depends on the thickness of the material that we have. So when we have thin films, it's better to use this kind of sample holder, like this one, where this one is this one, okay? So you can see here that this one is a thinner film compared to the sample here, okay? This is a dual cantilever, where essentially it's that one, okay? This one is for compression. This is a dual. And this is for shear. The possibilities really to use different kind of samples and different types of holders are quite wide for dynamic mechanical analysis, and that gives us a lot of flexibility, even though the information that we obtain generally is not too different, okay, with using different sample holders or different measurement techniques, okay? Yeah, so in terms of its standard use, its basic operation of DMA, we apply sinusoidal varying stress, and we measure the deformation, okay? The stress is usually applied at a constant frequency, but we can also do a multi-frequency test. So in this case, we assess the properties as a function of frequency, while the oscillation amplitude is held constant. Anyway, these are not too important for you. The two, as I told you, the two main test modes are temperature sweep and frequency sweep test. Temperature sweep is the most common. Okay, it's a measurement method where essentially what we do is we keep the frequency constant, and we ramp Usually we use much smaller heating rates than DSC. We use rates from 1 to 5 Celsius degrees per minute in order to have enough time to essentially obtain a good resolution of the tests, okay? And the second mode is a frequency sweep, where essentially what we do is that we keep the temperature constant. Keep T constant. And second, what we do is we variate omega. Now, I use this slide to show you that some people use DMA to measure. Of course, we use DMA to measure the glass transition, but sometimes they use different parameters of the DMA measurement, which are wrong in order to obtain the glass transition. What we have said already is that the glass transition is given by the peak of the tan delta over temperature, or approximately the middle of this, essentially the middle of this significant downshift at when the material softens completely, okay? So some people also claim that the TG can be obtained by the onset of this significant downshift, which is wrong. And also, some people are saying that the information that we can get from DMA is not only the storage modulus and the tan delta, but something else that is called the Lost Modulus. The Lost Modulus is essentially the ratio of the viscous component to stress, and essentially is related to the ability of a material to dissipate stress through heat. But so those people are claiming, some people are claiming that we can obtain the TG by the peak of the Lost Modulus, which is again wrong. And you can see how big difference is between the peak of the tan delta or the middle of the storage modulus versus temperature graph, where it shows a big downshift, a big slope. In this case, we have a -2 Celsius degrees glass transition, while the other two methods, they give us a glass transition of -30, which is wrong, okay? -28 and -30. So anytime someone asks you to identify glass transition from a storage modulus or the tan delta or a DMA measurement in general, you obtain, you use these two parameters that we discussed. Either the middle of this downshift, this yellow line, sorry, or the peak of the tan delta. Okay. Now, when we reinforce polymers, such as with materials, two-dimensional materials such as clays, of course, clays do not have as huge modulus as other 2D materials such as graphene. But still they can reinforce an epoxy. As you can see, there is an increase in the modulus as a result of the presence of the nanofillers, and also there is a shift of the TG. Usually the reason for the shift of the TG to higher temperatures when we're using nanofillers is because of confinement of the chains. From nanofillers. So what these nanofillers do is essentially they confine the chains. They do not allow them to move as freely, and as a result, they need more energy in order to obtain higher mobility, in order to allow these conformational changes and passing through the glass transition temperature. Okay. Yes, this is what we said about the elastic response again, and how it's reflected in the DMA. As we can see, we provide dynamic strain and we obtain dynamic stress. They're both sinusoidal, so they are in phase. Okay. In viscous response, we can see that these are out of phase. So you can see that the difference in the amplitude is 90 degrees here for a viscous material. Okay, so all energy that is applied is dissipated. And finally, for the viscoelastic material, we have a part of the energy that is applied that is dissipated. Okay, we again provide an excitation, and the response is given as a function of the loss angle. Okay, and this loss angle is essentially providing the tan delta versus temperature graph, which gives us the glass transition. So yeah, for an elastic response, we can see that the angle between the stress and the strain is 0. For a Newtonian liquid, for a viscous response, essentially, we have the two of them being out of phase. The shift between the stress and the strain is equal to P over 2. And finally, in the viscoelastic response, the phase angle is ranging between 0 and 90 degrees. Okay. And finally, the information that we get from the glass from the DMA is the storage modulus. Wherever you see G substituted with E, I don't know why I used G in this case. Some people use they use the G letter to show the results from DMA, but usually the most common one is E. Okay, the storage modulus, which is the same with elastic modulus. The loss modulus, which, as I told you, is the ratio of the viscous component to the stress, and essentially is related to the material's ability to dissipate stress through heat. And finally, the ratio of E double prime over E equals to tan delta. Okay, and that is pretty much it. Let's take a break now. That is the information that we obtained from DMA. Let's take a 10-minute break now. We will continue with a couple of multiple choice questions, relatively quick, and one problem on viscoelasticity, and we're done for the day. Okay, so 10-minute break, and I'll see you in a second. Okay, let's get started with revision on the mechanical property section, session 8, essentially, chapter 8. And let's start with question number 1. What does the area under the stress strain curve provide? Let me, question 1, A, B, C, and D. Initiate vote. Done for the materials. Go to the polymers. Okay, is it the energy to break? Is it the energy to elastically deform the material? Does it give the impact strength of the material or the compliance of the material? I give you 1-2 minutes. One more minute. Okay. I will end the vote now. So the polymers group, 60% said A and 40% said B. Let me check the materials group. Very similar, and this vote, 61% said A and 32% said B. Of course, the correct answer is A, okay? If we have a stress strain curve, it looks like that. If it looks like that, it doesn't really matter. The area under the stress strain curve gives us the toughness of the material, which is essentially the energy that is required to break the material. And we said that toughness is given by the integral of starting from 0 to the strain of fracture, sigma dE. Okay, a lot of you said B, but B says elastically deform the material. Elastic deformation takes place only in this initial part. Okay, so the initial part has to do with resilience, as we said. Okay. Okay, that is question number 1. Now, question number 2. What are the units of resilience? Resilience, we said, is the area under the elastic part of the stress strain curve. Question number 2. A, B, C, and D. Question 2. A, B, C, and D. 30 more seconds. Okay, let me end this one and vote. So for the polymer group, I have 62% for C, 32% for A, and then I have a couple of answers for B and D. So it's obvious that some of you realize that there's not only one correct answer, which is great. Let me see for the materials group and vote yes. Slightly less people voted for both A and C, which are the correct answers. Both A and C are the correct answers because 1 joule equals to 1 Newton per times meters, okay? So joule per cubic over cubic meter is equal to Newton over square meter, okay? And the resilience, we said, is the integral from 0 to the yield point of modulus times strain over strain. Okay? What is the effect of increasing strain rate on the strain at break? Q3, A, B, and C. To the polymers. Q3. Q3, A, B, and C. 1 minute for that, it's a very quick one. Okay. Very well. The polymer group, 95% of the people said A. Check the materials. 92% of the people said A for the materials. Indeed, the effect of strain rate or the strain at break, essentially what it does is decreases the strain at break. Also, the decrease of temperature has the same effect, okay, because it makes the materials behave as glassy. similar to glassy polymers. Okay, the chains are frozen, or we apply very fast strain, so chains are not able to orient themselves along strain direction. Okay, there is not enough time for the chains to be able to orient along the strain, and because of entanglements and because of the high strain rate, the strain at break is significantly decreased. Strain at break, and as a result, of course, toughness. Okay, question number 4. What is a characteristic of the mechanical properties of thermosets? Vote for question 4. A, B, C, D. Polymers. Question 4. A, B, C, and D. I repeat that in the exam, in the multiple choice questions, there will be only one correct answer, okay? In all the exam questions, make sure that you read very carefully the definition of the question. There might be, not just by myself, but by other teachers as well, there might be tricks being played to confuse you a bit, okay? So understand completely what it says on the definition of the problem or the question. Okay, let me check your answers. Okay, I don't see any more answers, so I'll end the vote. So the polymers group said 73% said C. Some people said 40% said B as well, which is obviously good because they got a memo that there's more than one correct answers. Some people also said A, which is obviously wrong. Let me check the materials group. Materials group, I think they did it slightly better. 60 and 55% said B and C, which are indeed the correct answers for a thermoset. The stress strain curve usually looks like that, okay? Because of the presence of crosslinks and very strong bonds between the chains, the three-dimensional network between the chains, it does not allow the polymer to elongate a lot. So the polymer has generally high modulus and a low strain at break, okay? And because it has low strain at break, it has brittle behavior and a high modulus, as we said. What is the contribution of intermolecular resistance to the mechanical properties of entangled or cross-linked glassy polymers? Question 5, A, B, C, D. B, C, D. Okay. One more minute. Okay, let me end it. So for the polymers group, the results were quite shared between answers. Let me check the materials group. I'll give you the answer. Same here. So in this case, the correct answer is contribution to modulus and contribution to yield. We said for an amorphous, a glassy polymer that can form a neck, stress strain curve looks like that. If we decompose this curve into two elements, we have the contribution of the intermolecular resistance. Okay, this is the intermolecular. And also we have the contribution of the network element component. As you can see, the network component corresponds to contributions regarding strain hardening and ultimate tensile strength, because essentially it provides the ultimate elongation and the ultimate strain hardening, while the intermolecular resistance contributes to the original part here, which is the modulus, and also here, which is let's say the threshold for plastic deformation. Okay. Question number 6. What is a process that includes extreme localization of strain? Question 6. A, B, C, and D. 30 more seconds. Okay, I end this. Indeed, the majority said C, which is the correct answer. Yeah. So extreme localization of strain takes place in crazing. Okay. Necking is not as highly concentrated strain localization. Okay. Because the strain is distributed along the neck, while in crazing, the strain is essentially localized in these nanoscale regions, nanocracks, as a result of crazing, and failure is initiated very early. Okay. Question number 7. What is the effect of short chains on the ultimate tensile strength? Question 7. A, B, and C. One minute for that. It's very simple. Okay, let me end the vote. So for the polymer group, 82% said B, which is indeed the correct answer. The materials group, maybe better, maybe more. Yeah, 97% said B. So yeah, indeed, B is the correct answer. Salt chains make the polymer decrease its ultimate tensile strength, because, as we saw, the stress strain curve can look like that. And for short chains, because they can disentangle much easier, they show a decreased ultimate tensile strength. Lower entanglement density. Okay. And finally, questions 8, 9, and 10. Let's say this is A, this is B, and this is C. Okay. Which of the three curves represents a semi-crystalline polymer? Question 8. B, C. Materials. Go to polymers. Only 30 seconds for that. What do you mean? You cannot see question number 10? Ah, sorry. I didn't notice I had that there. Okay, sorry. So indeed, okay, the correct answer for 8 is B, as all of you have said. Where's the question? And vote, yes, very simple. And get the question for the materials as well. Vote, indeed, the B is the correct answer. Which of the three curves shows the highest modulus? Question, it takes more time now to add the question rather than to answer. A, B, and C. Time sheet. Indeed, A is the correct answer. All of you have answered correctly. And finally, I will not be setting this as a question, individual one, but send any suggestions you have in the chat. How can we increase the toughness of the polymer represented by the blue curve if we say that the blue curve shows a polystyrene sample, let's say? Any ideas? How we can increase the toughness of A? Curve A. Anyone? See no answers from materials. What about polymers, people? A couple of nice answers, indeed, from the polymers group. Give 1 more minute to the materials, people. Anyone from materials? Yep. Indeed, rubber particles or plasticizers, or in general, blending with softer polymers is a very efficient strategy, essentially. So an answer can be incorporation of adhering rubber particles. And what do the particles, those rubber particles, do? Is essentially initiate many deformation zones. And secondly, they stabilize cracks or dissipate crack growth. Indeed, the increase of temperature, I saw a couple of you mentioned the increase of temperature or decrease of straight rate. It can be a way to achieve that, but overall it will not achieve as high toughness as the incorporation of rubber nanoparticles, because still the chains in this case are highly entangled, okay? And the entanglements will be causing us significant problems even if we supply a certain amount of thermal energy to the chain. But yes, certainly increase of temperature can be considered as a correct answer. And a very quick problem on viscoelasticity, and that's it for today. So we have a ring-shaped seal that is made from a viscoelastic material, and it is used to seal a joint between two rigid pipes. When incorporated in the joint, the seal is held at a fixed compressive strain of 0.2. Determine the time before the seal begins to break under an internal fluid pressure of 0.3 megapascals. It can be assumed that the relaxation time T0 of the material is 300 days. The short-term instantaneous modulus is 3 megapascals. So what we want is the time before the seal begins to leak. Okay? I'll give you 5 minutes for that, and I will provide you the answer. Anyone who solves this, I provide the answer onto the chat, okay? Daniel, I'm not sure what you sent me. Root 690. John, no. There is a mistake somewhere in your calculations. I see a lot of you doing the same mistake, which is a very silly mistake. I'll explain a bit in a second. The one that's more close is John, who has from the polymers group, who has a simple mistake. Materials group, anyone? Okay, let me give you the answer. So we're talking about relaxation, okay? Because we're saying that the seal is held at a fixed strain. So we're talking about relaxation. What equation gives us the most appropriate model for relaxation is the Maxwell model, which is equal to sigma 0 exponent of minus tau to tau 0. Okay? Well, sigma 0 is equal to strain times short-term modulus. So sigma 0 equals to 0.2 times 3 megapascals. This is a modulus, not sigma 0 as some of you put. So 0.2 times 3 megapascals, that is 0.6 megapascals. So the leaking pressure equals to 0.3 megapascals equals to 0.6 megapascals exponent minus T, and we know that the T0 is 300 days, okay? 300. So if you solve for that, therefore T equals to 208 days, okay? So the seal will begin leaking at 208 days. It's very simple. It's just a substitution of the correct values onto to the Maxwell model for stress relaxation. And that's pretty much it for the day. I promised we will finish earlier, but I'm sorry I didn't keep my promise. Any questions regarding viscoelasticity or mechanical properties or the essay? Please feel free to contact me. And that's pretty much it. Enjoy your weekend. Submit your essays on time. I repeat, the deadline is on Sunday. Please be on time, because if you don't submit it on time, then you will be hit with a penalty, okay? Enjoy your weekend, and I will see you next Monday. Bye, guys. Good to see you.